Just a short recap, what we discussed last time. So it was introduction to the topic of optimization methods, to the topic of optimization problems. So as you already know, uh, there are plenty of problems which we try to solve, for which we try to find an optimal solution in our everyday lives, in nature, in some organizations, to maximize certain thing. So the goal of the optimization is often defined as profit, reduction of cost, uh, lowest to lower the consumption of resources, increase income, minimize risk, uh, and so on and so on. So we can define the goals differently, and uh, this determines whether a given solution is optimal or not, because we are exploring some, it's called solution space, a feasible set of solutions that satisfy certain constraints, and according to uh, agreed conditions, we are trying to find an optimal solution. It is the one which mitigates the criteria for the optimality. And at the same time, there may exist different constraints which has to be satisfied in order to have the feasible solution. So these constraints may often come from certain, for example, certain production restrictions. So in the case of the production planning problem, we are trying to maximize the revenue, so maximize the income subtracted by the cost of the production. And for example, we have a limited number of resources which are delivered from our supplier. Also, we have limited ability to manufacture our product per day. So these are, for example, the constraints which may be introduced into the model, which can significantly complicate the solution, finding the solution of the problem. And today I would like to focus on linear programming. So as you can recall, it's a problem where we have only linear objective and constraint functions, and how to find a solution for such a problem using graphical methods. So how to draw the constraints, how to draw the feasible set, how to draw the goal function, and how to find the point where the function reaches its optimality. So just to recall, this is the formula for finding a static continuous function. Static, it means that the variables are not changing over the time. So we have to find such an x star, which is the minimum argument of a function f of x, which is our goal function, such that the following constraints are satisfied. And there are three types of constraints in general. The inequality constraints, so some left-hand side of the equation is lower or equal or greater or equal than 0. The equality constraints, so the left-hand side of the equation is equal to some constant. And range constraints, so they define the range of the variables. So given variable, for example, xi is greater than equal than the left-hand side of the equation, and it's lower or equal to the right-hand side of the equation. And also, just to recall, we can classify the problems into two groups, linear and nonlinear problems. The linear are easier to solve, and there are plenty of methods which are dealing efficiently with linear programming, especially the simplex method, which which can find solution by exploring the vertices of the solution space. On the one of the next lectures, I will describe in detail how the simplex method works and define why it's efficient. In the linear programming problems, both the objective function and the constraints are linear functions. And as I said, many efficient methods exist to solve such problems. And in fact, many difficult problems can be expressed as linear programming problems. For example, assignment of n people to n tasks. So we can deal with such huge problems where we have a huge number of possibilities due to the number of variables and permutation of these variables. We can, if we can formulate such a problem as a linear problem, it's often easy to find a solution for such a problem. And regarding the terminology, here is our optimization problem. We have an objective function, so this is the function which we want to maximize or minimize depending on the sign. And we have a decision variables. So these are the variables for which we have decided what values they will take. And these variables often are part of the objective function as well as the constraints. So the set of equalities or inequalities which have to be satisfied in order to find a feasible solution for such a problem. And there is often an assumption that the variables are non-negative. It's not obligatory, but in many real-life examples, the variables which, for example, describe the production amount or the, for example, road distance or amount of removed ground we're building the road, they cannot be negative. And if the variables are integers, then such a task is called integer linear programming problem. And unfortunately, such type of problems are more complex. However, there also exist methods to solve them, such as branch and bound or project cut or any other soft computing methods. So here is a given a standard form of the linear programming problem, and any problem can be reduced or converted to such a form. And I'm presenting you this form because some of the algorithms require that the programming problem is expressed in this form. So we have goal function. This expressed as a vector equalities. So we have cost, which is a vector of cost assigned to each of the variables. X is equal to, I will switch to a pencil. Sorry. Not Spotlight. Okay, I always forget where is the pencil in Zoom. Draw. Okay, here it is. So this is a vector, right? We have a variable x1, x2, x3, and so on. And this is our constraint vector, which is transposed. So it's equal to C1, C2, C3, and so on. And if we multiply, just quick recap from linear algebra, if we multiply those two vectors, we obtain C1 multiplied by x1 plus C2 multiplied by x2 plus C3 multiplied by x3, and so on and so on. So this is our objective function, which is composed of the decision variables multiplied by the corresponding costs. And we have a constraints which are expressed as equality constraints. In standard form, we only have equality constraints except the range constraints. So again, it's a vector equation. So we multiply the A matrix, which is coefficients for particular variables for each constraint, and we have right-hand side of the equation, which limits the variables to certain bounds. In standard form, the problem is a minimization problem. All constraints are equality constraints, and all variables are non-negative. And it is possible to convert any linear problem into such a standard form by applying certain by introducing certain additional variables, which I will describe later. And this form is contractual, however, it's used by many algorithms. It can be also described as follows: this equivalent to this form, except that here we have the inequality constraints. However, it's possible to convert equality constraints to inequality constraints. And we can switch between them if there is a need to switch between those forms. It is possible. And giving you some example regarding the linear problem, let's consider resource allocation problem. So we have a company which produces two types of copper cable. One has a diameter of 5 millimeters, and the second has a diameter of 10 millimeters. And these copper cables are produced on a single production line. So we have to choose which one we are producing with the following constraints. The copper which we obtain from the supplier allows us to produce 21,000 meters of 5 millimeter diameter cable, or 4 times less 10 millimeter diameter cable. So 10 millimeter diameter cable requires 4 times more resources to produce a meter of cable than the 5 millimeter diameter cable. And due to some business restrictions and demand, consumer demand, the weekly production or some storage limits, because these fibers have to be stored somewhere before selling them. The weekly production of 5 millimeter diameter cable should not exceed 15,000 meters, and the production of 10 millimeter diameter cable should not exceed 40% of the total production. And we have prices assigned to each type of cable, meter of cable. So the smaller cable costs 50 zlotys per meter, and the larger one 200 zlotys per meter. And our objective is to define in what quantities what kind of cables should be produced in such a way that we are maximizing the company profit. So first, what we have to do to define such a problem, we have to determine what are the decision variables. So we have two variables. X1 is the number of thousands of meters of a cable with a smaller diameter produced per week, and X2 is the number of thousands of meters of cable with higher diameter produced per week. Next, we have to determine the objective function. So we want to maximize the profit. To know what is the profit, we have to multiply the price for each meter of cable by the number of meters produced per cable. In fact, we should divide it by should multiply it by 1,000 because it's thousands of meters. However, whether we multiply the objective function or not, it will not change the objective function in terms of the point in terms of the values for the decision variables. It will only change the value of the profit, but it's still be the optimal function. So it doesn't matter in terms of solving the problem whether we consider that these are the thousands of meters or just meters, and if we multiply it by the profit multiplied by these thousands of meters, because it's a linear function. So if we multiply a linear variables in linear function by certain constant, is equal to in particular f of a is a constant multiplied by x is equal to a multiplied by f of x. This is the property of a linear function, so it doesn't matter in this case. And we have to determine the constraints. So we have the maximum amount of copper which we can produce, and it's equal to 21,000 of meters according to some business constraints, and the production of a larger diameter cable requires 4 times more copper than the production of a smaller diameter cable. And the production of a larger cable cannot be higher or equal than the 30% of the total production, which is expressed by this inequality. And production of a smaller cable cannot exceed 15,000 kilometers. And production of both cables cannot be lower than 0. So here we have our optimization problem, which we will try to solve. So intuitively, one should produce as much as a larger diameter cable because its price is higher. However, in this type of problem, there is equivalent profit in production of smaller diameter cable regarding the required resources to do so. So this is the one solution for the problem. So the number of thousands of meters produced for the first cable is equal to 15. So this is our maximum limit, and we can compute what value can be, what thousands of meters for the second fiber can be produced based on this inequality. And this is our profit in terms of thousands of zlotys. And as the price and cost of the copper used for both types of cables is proportional to the resource requirements is proportional to the cost, there are many solutions which are equivalent. So if we select another point for another value of produced thousands of meters for first type of fiber cable, and compute the remaining value, which can be used to produce the second type of cable, we obtain exactly the same profit. However, what will happen if we further increase the price for the second fiber? So if we slightly modify the objective function, the only difference is that we are the price for the bigger cable is 1 zloty higher for the 1 meter of cable. This is the solutions to this problem. So we should produce 5.73 thousand of smaller thousand of meters of smaller cable and 3.82 thousands of the larger cable. So this problem may look simple, and actually it is simple. It's very easy to solve. However, linear problems actually can be much more difficult. And another example to show you how to convert the description of the problem, how to formulate a mathematical model for a problem. So let us consider a company which produces windows, and these windows have to be delivered to stores in a period of 6 months, and in each month there is a different demand for the windows. For example, based on some agreement with the shop, they require different amount of windows per each month, and this is the amount of units required for each month. And the cost of producing one window in a given month is also different. It can be dependent, for example, on the change of the resources price or cost of the transporting resources, which is related to the fuel cost. So many different variables can impact the cost to produce one window. Of course, it's a little bit unrealistic example because we know in advance the cost. However, without such knowledge, such problems are very, very complex when we cannot predict how the variables will change in the future. In such a case, we have dynamic problems which are much harder to solve. So the storage of the produced windows for the next month is equal to 40. So we can store the cost of storage is equal to 40, and we should deliver windows minimizing the cost. So we have to determine the decision variables. Xi is the number of units produced in each month, where I is the number of months, and Yi is the number of units which are stored at the end of the corresponding month. And the objective function is related to first production cost. So the production cost is the cost of producing windows in each month multiplied by the amount of produced windows in each month, and cost of the storing the product. So it's the number of units held in storage multiplied by the cost of a storing single unit in a storage. So we are trying to minimize the production cost, which we have to add the cost of storing the products in a magazine. So we are trying to minimize the overall cost. And in each month, the demand for windows is equal to the number of windows which are available from the previous month, plus the number of windows which we produce in this month, minus the number of windows which are stored in the warehouse. So in the first month, we do not have any available windows from the previous month. We have to add windows which we produced in the first month, and we have to subtract the windows which we will store in a warehouse for the next month, and each should be equal to 100. So this is the production requirement for this month. In the second month, we add the number of windows which are held in warehouse in a previous month, plus the number of windows which we produced in this month, minus the number of windows which we will store in the warehouse. And it also should satisfy, it should be equal to the number of required units which we have to deliver. And this repeats for all the months. So these are our constraints. All the variables have to be greater or equal than 0, of course, because the production cannot be negative and we cannot store the negative number of windows in the warehouse. So the optimization model is as follows. We have to minimize over 6 months the cost of producing the windows and the cost of storing them in a warehouse, such that the following constraints are satisfied. So this is the production requirement per each month. The storage amount for the first month is equal to 0, and all the variables have to be greater or equal than 0. Where we have these two vectors, the first one defines the demands for the windows in each month. The second one defines the cost of production for windows for each month. So as you can see, the creation of such a problem, mathematical formulation is a little bit more complex than the previous one. Still, it is a simple problem to solve. However, designing a model can be a challenging part of the optimization process, especially for some complex phenomena which are related to some real life examples where we have many decision variables or many constraints, and often it's not simple to even define these constraints. So what is the economic interpretation of a linear programming? Linear programming is very popular in economic problems. So typically, our goal is to maximize the profit, the revenue under limited resources. So we have limited resources to produce something to maximize the profit. We have a set of constraints, and these constraints are related to the presence of certain types of production activities. So to create certain activity, which is the variable of, for example, our production component, we have to use some resources. We have M types of resources, which are needed in different proportions to create the production activities, and they are limited by certain quantity. So we have limited number of resources defined as a vector B. So the constraints defines the consumption of if resource type to produce a unit of product J, and it has to be equal to Aij. This is the value of the resources consumed, and the profit is the outcome from the production of each activity multiplied by the C, which is often a price for a certain activity. So The goal is to determine the levels of production, the volumes of each product, such that the performance of the production system is maximized or minimized, depending whether we are multiplying the objective function by -1. And as I already mentioned, these are the fundamental assumptions of the linear model. Maybe these are the fundamental properties of the linear model. So proportionality, it was visible in the first example in the selection of amount thousands of the selecting values for the production of copper cables, where the decision was irrelevant because we were obtaining the same revenue. So the proportionality, resource consumption is proportional to the level of production using the resource. So if we increase the production of certain resource by a given factor, the resource consumption also will increase by the same factor. And additivity, so consumption of resources, is the sum of the consumption of resource of a particular resource by all individual products. And often, which is not mandatory, is the non-negativity, so we cannot have negative output. And another example is related to task scheduling. So let us assume that we have 3 machines, and we have to assign 7 tasks to those machines in such a way that the total execution time is minimized. Each task takes certain amount of time. So the goal is to minimize the total duration. And in this example here on this chart, these 7 tasks are completed in time slot units on 3 machines, and we should ask ourselves whether this is optimal solution or not. And obviously it's not. It's easy to create a solution which is which has lower objective function, lower total duration. So after ordering, it requires 8 units of time. And again, we can ask ourselves whether it's optimal solution or not. And it's easy to deduce that it is actually optimal because we have 3 machines, we have 7 tasks. The summary time required to complete all those tasks is equal to 24. So if we spread evenly those tasks on 3 machines, it requires 8 units on each machine. So this is the optimal solution, because if we will reduce the time consumed on one machine, we have to increase it on another, and we cannot increase it on any machine without exceeding this total duration of 8 tasks. So in this problem, the solution space is equal the number of machines multiplied to the power of number of tasks. So it's equal to 3 to the power of 7, which is equal to 2187 possibilities. So actually it's quite small problem. However, the important thing is the complexity of the problem, how it will increase regarding the increase of the variable size. So as you can see on these charts, this will happen if we increase the number of machines or number of tasks. So different colors represents the increase in the number of machines, and on the x-axis we have the increase of number of tasks which have to be realized on those machines. And this chart is using logarithmic scale on y-axis. This is the number of possibilities, the solution space, and here we have the zoomed fragment of this part of chart using linear scale. So how many possibilities do we have? And as you can see, if we increase the number of machines, the complexity, that the number of possible solutions increase very, very rapidly. And the same goes here, but it's less visible because it's a logarithmic scale. Because if we would use a linear scale on y-axis, the chart would look like this, probably. And it wasn't possible even to see differences between those lines. So how to create a model for such a problem? It's an integer programming problem because we have to take decisions, and decision is whether a given task should be realized on a given machine. So this is a decision, yes/no decision. Actually, it's a binary programming model. So let us denote T is the time, I is the task, J is the machine. So we have a variables xij, which is equal to 1 if a task I is assigned to machine J. And we want to minimize the overall time. And we have to introduce some constraints. The first constraint defines the overall time. So the overall time is lower or equal than the sum of times for task I multiplied by the decision variable. So if we assign certain task I to machine J, we multiply it by the time required to accomplish this task, and we calculate the sum of all tasks realized on machine J, and the overall time has to be greater or equal than this value. So in other words, we are iterating over each machine. So first we consider a first machine, J equal 1, and we complete the sum of times of tasks assigned to this machine. So if a task is assigned to this machine, it's equal to 1, we multiply it by time required for this task. If it's not assigned, it's equal to 0. So time required for this task doesn't matter. And we calculate the sum, and we have to assure that the overall time is greater than equal. And repeat this for all of the machines. So we create m such constraints, and the overall time has to be greater or equal than any of these times for each machine. And because we are minimizing the overall time, so it has a tendency to move this t value as low as possible. So it assures us that the inequality constraint is sufficient here, because let's assume that the summary time for machine 1 is equal, for example, to 8. This inequality assures that the overall time has to be greater or equal to 8. So the t can be equal to 10, 12, 15, or any other value which is higher than 8. However, as we are minimizing the overall time, the t variable, it drags it towards this bound, so it drags it towards the value of 8. So depending what is the highest value of each of these constraints for a machine, it drags this variable towards this value. So in such a case, it will be equal to 10, because we want to minimize this variable, so it will be as low as possible. However, it has to satisfy these constraints. And we have another constraint. It determines that a given task is assigned only to one machine. So we are repeating this for each task. So for example, we are considering a first task, and we check each machine, and we are checking if a given task is assigned to this machine. If it's assigned to this machine, it's equal to 1. If it's not assigned, it's equal to 0. And we are calculating sum of such assignments. And because it has to be equal to 1, it can only be assigned to one machine, and it has to be assigned to exactly one machine. So it cannot remain not assigned. And we repeat this for all of the tasks, just to make sure that a given task is assigned to exactly one machine. So as you can see, creation of such problem mathematical model can be a little bit complex. And as I already mentioned, the general task can be reduced to standard form. However, it can happen that we lose some efficiency, so we will increase the number of variables or constraints, but by converting such a model with inequalities into a model which has equalities only. And let me show you how we can convert such inequalities to equalities on here should be equalities on the right hand side. So let us first consider a full inequality constraints of type lower or equal. So here we have a vector equation. We have a vector of coefficients multiplied by variables, which is lower or equal than a certain constant, right? So it's a1 multiplied by x1 plus a2 multiplied by x2, and so on. It is lower or equal than b. And how we can convert it to equality? We can do so by introducing additional slack variable z. So if we add this variable to this inequality, we can change this sign into equality. And why is that? We have to make another assumption that this new variable is greater or equal than 0. So we introduce a new variable, and this part of the equation can be equal to any value lower or equal than b. If it's equal to b, if, let's call it left-hand side, if left-hand side is equal to 0 to b, then z is equal to 0, and the equality is correct. If, for example, left-hand side is lower than b, it's equal to b minus 5, then z is equal to 5, and again this equality is satisfied. So by introducing this variable, we can convert the equality into into inequality into equality constraint. Okay, I lost the pointer on the presentation. Okay, here it is. So similarly, for the full inequality constraints of the type greater or equal, we again can reduce it to equality constraint by introducing additional variable z. However, at this time we are subtracting this variable. So if it's equal to, if this part of the equation a multiplied by x is equal to b, the variable z is equal to 0. If it's higher, the z variable has to be greater than 0. So again, it is possible, but we are increasing the number of variables. Another example, we have two-sided inequality constraint. So our constraint is greater or equal to the lower bound, and it's lower or equal to the upper bound. We can convert it to two inequalities. So firstly, we are considering this part of the equation. Then we are considering this part of the equation as a second constraint, and we are introducing additional variables. So in such a case, we have to A transposed multiplied by x plus z1 has to be lower or equal than u. So we're introducing this variable, and for this equation, A transport multiplied by x minus z2 is greater or equal than L. So we have two new variables, z1, z2, and for both of them, we have to assure that they are greater or equal than 0, right? So this is how we can convert two-sided inequality constraint into equality. Sorry, here should be equality, of course. That was the point of introducing additional variables. And another example is two-sided variable range. So often we assume, for example, that x1 is greater or equal than 5 or any other, and at the same time can be lower or equal than 10, and so on. So in such a case, again, we are splitting it to two constraints. This is the first constraint, this is the second constraint. And again, we are introducing the slack variables. Maybe x1 a upper bound, xi minus z2i equal xi lower bound, right? So this is exactly this. We are introducing two slack variables. We can subtract this both equations to remove these variables. So in such a case, we have z1i minus z2i is equal to xiu minus xil. So in such a case, we are introducing two new variables, z1 and z2. However, we are removing this variable, so it's no longer needed. And if we have unconstrained variables, so it can take any value from the right hand side, so the plus infinity or minus infinity. We can also convert it to equality form by introducing the difference of two variables. So let's assume that xi is equal to z1 minus z2, both of them are greater or equal than 0, and we can assign any value for them. So by such two variables, we can obtain plus or minus infinity, so any value for the xi. And in similar way, any linear programming task can be converted to its standard form. It may result in introduction of large number of new variables. However, for certain algorithms, it's required that this optimization problem is expressed in this equality form. We can also revert the process. However, so we can convert an equality constraint into inequality form in such a way. However, there is no point of doing this because actually what we are achieving, we are increasing the number of constraints, and that's all what we accomplished. So at the same time, the left-hand side of equation is lower or equal than b, and it's greater or equal than b. So it doesn't make sense, but it's possible, of course. So what are the difficulties in solving linear tasks? So first of all, it's the solution space. So if we have n variables, this is the size of our variables. So let's assume that, for example, this is the number of machines or number of tasks is equal to n, and if the complexity of the problem is expressed by such value as 2 to the power of n or n factorial, these are the problems where the solution space is increasing very, very rapidly with the size of the problem. And for such problems, complete search, checking every possibility, quickly becomes impossible for even very small instances. Such a problems which has such a complexity are often in NP class problems. So these are the problems for which we cannot find a solution in polynomial time. So polynomial means that, for example, that we need, for example, x to the power of 3 plus 2 times x to the power of 2, and so on. This is the polynomial complexity of the problem. And we cannot find a solution in such a time. We can only verify that the solution is feasible in such time. So there is a lot of problems which are in this class, and for such a problem, using a brute force, a complete search is not an option because it's not possible to calculate them in reasonable time. However, many linear problems, if they are continuous, not integer, they are in polynomial class, and they can be solved using, for example, graphical methods. If we have only two variables for higher dimensionality, it's hard to draw. I mean, it's not possible to draw a feasible set and to check the optimal value by drawing level lines. So we have other methods such as simplex method or duality theory. So its duality is the option to find a similar problem. If we have, for example, a minimization problem, we can find a similar maximization problem, which is easier to solve. And by solving it, we are also solving a dual problem, so our primer problem, which was more complex. So we are finding a problem which is easier to solve, but the solution will be exactly the same for both problems. And Let me show you how the graphical methods work. So let us consider a following optimization task. We want to minimize such a function, 5x1 plus 2x2. And we have the set of following constraints. And this is our chart where we will draw these constraints and find the optimality of this function. So what is the first task? First task is to draw constraints. So we are taking the first constraint, 2x1 plus 5x2 is greater or equal than 10. And we are finding 2 points which satisfy this constraint. First of all, we assume that, let's just assume for a short moment that we have equality, and we have to find 2 points which satisfy this equality. So the simplest method is to put 0 under one variable and then calculate what's the value for the second variable. So it has to be 2, right? 5 multiplied by 2 is equal to 10. So we have a first point. First point is for x1 equal to 0, x2 equal to 2. So this is our first point. Then we are changing the approach and assuming that x2 is equal to 0, and we have to calculate what's the value for x1, and it's obviously 5. So the second point is in 5, 0. So we have 2 points. We have to draw a line between those points, and then we are considering the inequality. So we are forgetting that for a short moment we consider equality, and we are checking if we have greater or equal, it means that we are considering values on the right hand side of the line or above the line. So this is this region, right? So we draw our first constraint. So let us move to the second constraint. For x1 minus x2 has to be greater or equal than 12. Again, we assume that the first variable is 0. If it's 0, then x2 has to be minus 12. And because we assumed we draw such a chart, it's outside the scope of our chart, so we can select any other point and solve the equality. So let's assume that x1 is equal to 4. So here we have 4 multiplied by 4 is equal to 16. So we have to subtract 4 to satisfy this temporal equality that's equal to 12. So we have a point 4, 4. And for the second point, we can assume that x2 is equal to 0, then x1 is equal to 3. So we have 2 points, 4, 4 and 3, 0. And we have to draw a line between those points. So 4, 4 is somewhere here, 3, 0 is here. We are drawing the line between them. And as it's greater or equal, it defines the region right to this line. And we are considering the next constraint. And the approach is the same. We are assuming certain value for one variable, compute the value for the second one, assuming that it's equality. We obtain 2 points, connect them, consider the sign. If it's lower or equal, it means that's the left side of the line, or it's below the line. So this is our third constraint. And then we have a feasible set. So we also have to account for the range variables that x1 is greater or equal than 0 and x2 is greater or equal than 0. So we are rejecting this part of the feasibility set because x2 has to be greater or equal than 0. So here we have a feasible set. feasible set. So this is the region where we can look for the best value of objective function and assure that all the constraints are correct. So this is our goal function. We want to minimize 5x1 plus 2x2. So first of all, we should assume certain value. Let's assume that our goal function is equal to 30. If it's equal to 30, what are the values for this variables? We are finding 1 point, so we assume that x1 is, for example, equal to 4. Here we have 20, so 20 plus 10, so x2 has to be equal to 5, right? So we have 1 point, 4, 5, 4, and 5, somewhere here. It doesn't matter, it's outside the feasible set. Then, for example, we assume that x2 is equal to 0, then x1 is equal to 6. 6 multiplied by 5 is equal to 30. So we have another point here, right, 0, 6. We connect those 2 points, and this is our objective function level line. So this is the line where f of x is equal to 30. So it actually you have 1 point which is in this feasible set, and we want to find a minimum of this function. So if we compute for another value, for example, for 25, we probably will have another line somewhere here which is parallel to this one, where f of x is equal to 25, and so on, so on. So we are moving the goal function towards the optimum. So we are moving it in that direction until the line will touch with the last point in the feasible region. So this will be this point here, obviously. So right, I will clear the chart. This is this line drawn by assuming that f of x is equal to 30 when we are moving it towards the optimum. So it's exactly here, and to find what is this value, because it's hard to read, it's some fraction on the x-axis, we have to solve the equation considering these two constraints which are involved in this optimum value. So first constraint is the blue one, the second one is the light blue one. So we assume that there are equalities because this point is exactly on the constraint line. So the point has to satisfy this equality because it's on this constraint line, and it has to satisfy this equality because it's on this equation line. It's here. So if we subtract these equations, we obtain, first multiply this by 2, so we have 4x1 plus 10 x2 is equal to 12, right? This is this equation. If we subtract them, we obtain 9x2 is equal to 8, so 4.5 x2 is equal to 4. Thus, we can calculate what is x2. It's equal to 0.88. And inserting this into the second equation, so into this one, we can calculate what is the value of x1. And after that, we can insert them into objective function to check what is the value of objective function. So this point is 322, 0.88, and value in that point is equal to 1084, right? So this is how it works, the graphical method. So let me show you one more example. We have a maximization problem. The goal function is 2x1 plus 2x2. We have a set of constraints, and the steps are the same. We are considering the first constraint. We are evaluating 2 points which satisfy the temporal equality for this constraint, and then we are checking the sign. It's greater or equal, so it means that it's the right-hand side of the line. We are checking another constraint. Again, calculating 2 points, connecting them, checking the sign. So we are interested what is below the line. The third constraint and similar process. So we have our feasible set here. Then we are taking our goal function and assume certain value for this goal function. Let us assume it's equal to 4, and we are computing 2 points for this function. So we have a level line. So all the points on this line have the objective function equal to 4. And we are moving this line towards the optimum, so we are maximizing it. So if we have the maximization problem, we are moving it such the goal function increases. So we are moving it upwards until it will touch the last possible point in the feasible region. And in this example, it happens that these lines are parallel, the line is parallel to the constraint. So in such a case, we will have multiple points which are optimal, which has the same value. So we have a set of global optimals, and to solve the range of points which satisfy which has the optimal value, we have to consider intersection of this constraint with optimal points. Sorry, with 2 constraints. So the first constraint is that x1 is greater or equal than 0. The second constraint is this green line. So we have a set of 4 points, and by subtracting the equations, we obtain here it's easy, right? X1 is equal to 0, x2 is equal to 5, and we are solving this. Our first equation, it's here. And in the second pair of equations, so it's this line with this line, we are finding this point intersection of these constraints. We are subtracting these equations, so x2 is reducing. We have 2x1 is equal to 7, so x1 is equal to 3.5, so x2 by inserting, for example, into this equation is equal to 1.5. So this is our second point. We have 2 points. The first one is obviously this. It could be easily read from the chart that this point is equal to 0.5, and we computed this point is equal to 3.5, 1.5. So the function has maximum on the section between those 2 points given by the line x1 plus x2 is equal to 5. This is this constraint. So this is this line x1 plus x2 is equal to 5. This is the function of this line. And we have a defined range for which the function takes the optimum values regarding the feasibility set. So by inserting any of these points or any other point on this line into the function, we obtain the function value. So if we, for example, insert this point and compute the objective function, we know that f of x on this line is equal to 10. So this is our objective function. And 2 more examples. The first one is the contradictory task. It may happen that there is no existing any solution to the problem. So let us consider the following optimization task. We have the minimization, such that the following constraints have to be satisfied. So if we draw these constraints, we can observe that the point should be below this line, and at the same time, the point should be above this line. So the feasibility set is empty. Our set feasibility is empty. It doesn't contain any points. So it can be a case, let's say it's trivial in case of two dimensions. However, let's assume that we have many variables. It may not be obvious that there is no existing any feasible point for a problem. And the second case is the infinite task. So we can increase the values of variables endlessly, so the value of objective function is improving. So we have such a problem. If we draw those two constraints, it's here, and this is our feasibility set, and this is our objective function. As it is maximization problem, we are moving it upwards to increase the value of the objective function. And if we assume certain lines, certain value, let's assume that f of x is equal, for example, 30. Here we can move it farther, we can move it farther, and so on. So it's infeasible, it's infinite task. We cannot determine the value of variables because we can increase them without violating the constraints. So this is the third type of the solution of the problem. So what are the limits of the graphical method? To conclude this talk, first of all, it's very limited because it is applicable only for two variables. It's not possible to solve more dimensional problems with this method. It's, as you saw, it's time consuming because we have to draw constraints, we have to think whether it's above or below the constraint, find the feasibility set, draw the level lines of the objective function, and move this objective function towards optimum. And the highest disadvantage, I suppose, is difficulty to automate. It's not possible to create a tool, or it would be very hard to create or inefficient to create a tool which will draw the lines and move the lines and try to find the optimum in such a way. So it's easy for us for simple problems to solve them in such a way. However, for example, developing a computer software to solve the optimization problem, this method it's not applicable at all. And the other constraint is that it doesn't work for nonlinear problems. And it is because for linear problems, the function is predictable and we can move the level lines. In nonlinear problems, it's not possible. So maybe I will explain a little bit more on the next talk. But I suppose it's quite intuitive that for nonlinear problems, it's not possible to solve them graphically because we do not know how to move this objective function level lines. In linear problems, there is always a direction in which we can move the objective function. So let us assume that we have such three-dimensional space. These are our variables. This is our objective function, or f of x. We have certain constraints, for example, here, right? This is our feasibility set. And as the objective function is linear, it has to be some kind of a plane in three-dimensional space, right? So if it is a plane, we can always draw a certain line in a feasibility set, which has a certain value in our objective function, and we can move this line in such a way that we are improving the value of the objective function until we reach some point. And if the function would be non-linear, for example, something like this, right? Then if we are at certain point here, we do not know whether we should move level line here, or we should move this point here or there, right? Because the function is non-linear, it's not predictable how the value of the objective function will change when we move the investigated point. So let me finish with this conclusion, and thank you for your attendance, and see you or hear you next week.
Thank you.